All of you welcome in our next period. We see the theorem cancellation law for multiplication. The law is given by if xy equal to zy, then we get x equal to z. For every x, y, z belongs to R and y is not equal to 0. Consider the left hand side and prove that right hand side. Therefore, consider xy equal to zy. Equation 1. Since y is not equal to 0, therefore inverse of y, that is y inverse, exists. Therefore, multiply equation 1 by y inverse on both sides. Therefore, x1 into y inverse equal to z1 into y inverse. Then by associative property, we associate y into y inverse. Here also y into y inverse in one bracket. Therefore, x into y inverse equal to z into y inverse, since by associative property. Again, by existence of inverse, we have y into y inverse equal to 1. Also, here y into y inverse equal to 1. Therefore, x into 1 equal to z into 1. Therefore, x into 1 we have x and z into 1 we have z. Seen by the property existence of identity element. If we multiply the element by 1, then we get the same element, that is the identity element 1 is exist. Therefore, we start with this xy equal to zy and y implies at x equal to z. Therefore, xy equal to zy implies x equal to z, hence the property proved. That is the cancellation law for multiplication is proved. Now we see the second theorem. Unique solution. That AB belongs to R, then the equation given by this Ax equal to B has a unique solution given by x equal to A inverse B. If we take A on the right hand side, we get 1 by A, that is A inverse B. Therefore, this equation has the solution x equal to A inverse B. We see the proof of the theorem. Consider the given equation Ax equal to B, given equation. Then A is not equal to 0, therefore inverse of A exists. Therefore, we multiply both sides this equation by A inverse. Multiplying equation x plus x equal to B by A inverse on both sides. Therefore, A inverse into A into x equal to A inverse into B. Then by associative property, we associate this A inverse A. Therefore, A inverse into A in one bracket into x, seen by associative property. Again, by existence of identity inverse, we have A into A inverse equal to 1 by existence of inverse element. Again, by existence of identity element, if we multiply any number by 1, we get the same number. Therefore, x equal to A inverse B, seen by existence of identity element. Therefore, we start here by this equation x equal to B and we get x equal to A inverse B. Here we start the equation x equal to B and we arrive at x equal to A inverse B. Therefore, we say that the equation ax into A into x equal to B has a unique solution given by this x equal to A inverse B, which proves the theorem. Then we see the one example. If A and B are non-zero in R, then AB inverse equal to A inverse into B inverse. see the solution. We consider the left hand side AB inverse, and we multiply this AB inverse by A inverse B inverse. Since A and B are non-zero in R, that is A is not equal to 0, B is not equal to 0. So A inverse and B inverse exist. Therefore, we multiply both sides by A inverse into B inverse. Then we consider the left hand side AB inverse, consider the LHS and multiply the LHS by A inverse B inverse equal to, then we write AB inverse into, by commutative property we have AB equal to BA, now we write here this AB equal to BA, since by commutative property. Now take this AB into A inverse, B inverse like this. Then we associate this E and A inverse in one bracket. Therefore, B into A inverse into B inverse, since by associative property. We know that A into A inverse, we have 1 in multiplication. Therefore, B into 1 into B inverse, since by existence of inverse. Therefore, B into 1 we have 1, therefore B into B inverse, since by existence of identity element. And B into B inverse we have 1. Since existence of inverse element, therefore I get AB into A inverse B inverse equal to 1. That is why I get multiplication of these two numbers equal to 1. That is why I say that inverse of this AB is A inverse into B inverse. That is inverse of the first element in the second element. Implies inverse of AB is A inverse into B inverse, or in terms of sign we write it as AB inverse equal to A inverse into B inverse. That is the example is proved, that is AB inverse equal to A inverse into B inverse. Then we put the next theorem. If AB belongs to R, then first A into minus B equal to minus AB. Second, minus A into B equal to minus of AB. Third, minus A into minus B equal to AB. Proof. First, we know that by the addition of negative B plus minus B equal to 0. Say by addition of negative, this implies we multiply by A on both sides. Multiplying by A on both sides, then by associativity we can make them simplifying AB plus A into minus B equal to A into 0, we get 0. Same by distributive property, and A into 0 equal to 0. Since A into 0 equal to 0 and distributive property, we distribute over this bracket by A. Now from this we say that A into minus B equal to minus AB. We take this on right side, therefore A into minus B equal to minus of A. Therefore the first is proved, A into minus B equal to minus of A. Now to prove second, we interchange A and B in equation 1. Interchanging A and B in 1. Therefore interchange your A in place of A, write down B minus A equal to minus B A. Again AB equal to BA, we have by commutative property we interchange minus A into B equal to minus AB, since AB equal to B by commutative property. Therefore we prove the second, minus A into B equal to minus of AB. Now replacing B by minus B into